show that net force is equal to delta P over delta T, which you can really interpret as the time rate of change of momentum. If you've taken any calculus, you might know that time rate of change is a very calculus kind of concept, but we're not in this class going to do it in a calculus way. We're just going to think about it as like, a change in momentum divided by a change in time representing a time rate. It's kind of like, like a slope of a line can be interpreted as a rate, right? Like a delta y over delta x is some kind of rate, but we just have different symbols here. But how do I relate this to Newton's second law? Because when it says show this, I think this is related to Newton's second law. So if I, maybe the way I'll do this is I'm going to start with just looking at delta P. There's probably different ways to do this, and this slide is going to show us one, and I haven't looked at it, so I'm just going to do it right now off the cuff and see what happens. So I'm saying let's start by looking at this and analyzing what that might really mean. And so if I say change in momentum, I'm really talking about the change of mass times velocity per some change in time. But I think it's reasonable to say that if you have a change in the mass times velocity, in that sense, like if I said, hey, I've got 1,000 kilogram vehicle that is going at 10 meters per second, and then now I speed it up to 20 meters per second, right? Well, I would take 20 times 1,000 minus 10 times 1,000 to get the change in momentum. But I could also have stated that as 1,000 times 20 minus 10. So let me write what I'm saying here. So I said, again, this was the mass, was 1,000 kilograms times, say, 20 meters per second, right? This I thought of as representing final momentum in this example I just tossed out here, okay? And then I said, well, if you want to find the momentum change, given that it's sped up from 1,000 kilograms to, sped up from to 20 meters per second from 10 meters per second. How do you speed up to 1,000 kilograms, right? That didn't really make much sense. Anyways, I think I was looking at this number as I said that. But what I'm trying to say, is if this is the initial momentum here, the second quantity, this is what I would do, right? This really is the change in momentum, right? Hopefully we can all agree to that. But the thing I might notice is like, since the mass really is the same for both final state and initial state, there is like some rule in math, right? You remember what that rule is? If you do, maybe send it to me. Let's see. I think it has something to do with distributive property, right? It's kind of like backwards distributive, right? Because to go from this step to here, you'd distribute the 1,000 kilogram on both of these, right? But you're basically factoring out a common term. I think that's what they say in math class, right? Anyways, but if I were to write that into this formula up here, right? Because this represents, right? This thing I wrote here really represents just the change in mass times velocity, reflecting the reality that generally we're not seeing changes in masses when we're looking at changes in momentum with mass times velocity. This one here, though, I think you could write as that mass that's not changing multiplied just simply by the change in velocity. So that's what I'd like to do up here is just say, okay, change in mass times velocity is really just mass times change in velocity. So sometimes when you write it in symbols, it can seem a little like too much abstract symbol manipulation. So I wanted to do this example here just to make it a little bit more real for all of us and see that I'm not really cheating here. But what's cool about this, though, is maybe if I rewrite it with the m in front here, delta v over delta t here, this is the time rate of change of velocity, which is how we defined acceleration. So this is mass times acceleration, and Newton's second law says that mass times acceleration is equal to net force. So really, since I started with delta p over delta t and I wound up with net force, what I have shown here is that the net force is equal to the time rate of change of momentum. Anyways, that was my messy version. Let's see what the slide says. And I think it kind of just showed really quickly the same math I did here. We took a little more time to explore it on the whiteboard. And then said, by Newton's second law, this implies that the net force must be equal to the time rate of change of momentum delta P over delta T.